With respect to the definition of a digital signal, we'll describe an end-to-end system with input and output in the analog worlds, but processing performed in the digital world. Let us first define what is a signal. A general definition is that it is a function and one-dimensional, an x of t, for example, function, t is the independent variable, or a two-dimensional x of t1, t2 are the independent variables, that contains information. It tells us something useful about the behavior or the nature of some phenomenon of interest. In the physical world, we can say that any quantity that changes with respect to time and or with respect to space is potentially a signal. So the speed of a moving car represents a signal. The pressure that I apply on the gas pedal of the car is a signal. If I go and measure the height of the buildings in a city, then this becomes a two-dimensional signal, tells us at each location what the height is, and so on and so forth. Another example here is the price of the oil over the years. So the independent variable is time. The horizontal axis here is time in years, and the vertical axis is the price of oil in dollars and cents. It goes up, as we all know and expect. Similarly, here is an EKG signal, an electrocardiogram. Again, here is time on the horizontal axis and the amplitude of the signal on the vertical axis. So a signal like this shows the health of somebody's heart. Signals and systems play a very important role in many areas of science and technology, from communication to aeronautics, astronautics, to circuits design, biomedical engineering, and so on. Clearly, in this class, images and videos are the signals of interest we'll be dealing with. We have analog and digital signals. To put them in some perspective, let's look at a speech generation, transmission, processing, perception system like the one depicted in this figure. So speech is generated by the pressure provided by the lungs that becomes sound in the glottis in the larynx, which is then converted into vowels and consonants by the vocal tract. Speech is an acoustic signal that is transmitted through sound waves utilizing the vibration of the air molecules. So here we have an acoustic signal. So such a signal reaches a microphone here, which is a transducer. It converts one form of energy, acoustical energy, into another form of energy, electrical energy. So here I have an electrical signal. Both these signals are analog signals or continuous signals. If I take a kind of toy example here, such a signal, let's say, looks like this, where here is the time axis and here x of t is the amplitude of such a signal. This is an analog signal because the independent variable t as well as the amplitude x, which is a function of t, are continuous numbers. Now I want to process such a speech signal by a digital computer. And this is really the objective of any digital signal processing class. And digital computers only understand zeros and ones, or understand digital signals, and therefore I need to convert my analog signal into a digital one, which is the function of this A to D converter box. In doing so, converting an analog to a digital signal, one has to take two steps. The first step is to sample the signal or discretize it in the time domain. This means that I look at the values of the signal at equally spaced points, so at value at time 0, at time capital T, at time 2t, 3t, 4t, minus t, and so on. So now I have the values of the signal here at this time instance, this time instance, and so on. So I have converted my signal into a discrete time signal through the process which is called sampling. The second step is to discretize the amplitude of the signal. This means that I have only certain values available to represent x of t, integer values. So let's assume that the values I have available are this one, this one, this one, this one. This means that, so let's call this 0, delta, 2 delta, 3 delta. So this means that this value here at 0 will be represented by this value. The second value will be represented by this value. Similarly, this one will be represented by this value. This will be represented by 0. And this one will also be represented by this value. Okay? So through this process that is called quantization, I have now a discrete amplitude of the signal, right? So the value at 3t here is the quantized value of x at 3t, right? Actually, here will also be the same value, x quantized at 4t, while the actual value here, this is x of 4t, right? And after quantization, it becomes the blue value. So clearly, quantization introduces an error. So after both sampling and quantization, I end up with a signal that has both its independent variable as well as its amplitude being represented by discrete values. And such a signal is called a digital signal. Okay, so this signal is an input to the computer, which is going to process it, and then at the other end, I follow somehow the reverse order. In other words, the signal is turned from digital to analog through the converter shown here. Then this analog signal reaches another transducer. This is also called an actuator that will turn the current into a vibration and therefore into another acoustic signal, which is going to be perceived by the human auditory system. So here again, I have an electrical signal, and this is again an acoustic signal. The objective of a digital signal processing class is to focus onto the central part here, right? To focus on the techniques that will allow us to manipulate digital signals to perform certain tasks that depend on the application. So we see here that we have two worlds. We have the analog world here and here, right? So analog here, and the digital world or the digital domain here in the middle that is of our primary interest. A similar situation to the previous one is depicted by this block diagram that shows the generation, recording, processing, and sensing of an image. So electromagnetic energy in the visible part of the spectrum is leaving the sun, reflected by the object, travels through the air, and reaches here a sensor, a transducer, which is an analog camera that through photochemistry converts light energy into chemical changes on the film. Some of you might be too young to remember analog cameras that were using film, but there's still some around in existence. So the brighter parts of the image have higher concentration of silver halide grains, and this film, after it's processed, negative or black and white film, represents an analog image. So again, my objective here is to process the image by digital computer, and therefore I have to convert my analog image to a digital one through this A to D block. In this particular case, I can use a densitometer that measures the concentration of these silver halide grains on the film, or a scanner to end up with a digital image. Of course, nowadays, direct digital systems are prevalent, which means that these two units here are grouped together, and this becomes a digital camera that we are all familiar with. So I guess we should put here that this in here is an analog camera. After the digital image is processed by the computer, and again, this is the main objective of this class. We'll talk about techniques that will allow us to process digital images. We want to take the processed image, and in many cases, we want this image to be seen by the human viewer. So the reverse path is followed, whereby the digital image is converted into an analog one, and this then signal will feed into a monitor, an analog monitor, such as a CRT monitor, that will convert the image into an electromagnetic wave that is going to reach the human visual system, the eye of the observer. Again, nowadays, digital monitors or flat panels are prevalent. So an LCD here will be fed by the digital signal directly. A video adapter plays the role of the D2A converter. So in this class, we'll say a few things about sampling and quantization of images that are represented by this A to D block, and actually could be resampling or requantization, as we'll see. We'll say a few things about properties of the visual system, but by and large, our main focus is in this center block, where the input is a digital image and the output is another processed digital image one. To demonstrate sampling, or better yet, resampling, let's consider this digital image. It's a 256 by 256 image, which means it has 256 rows and 256 columns. And it's an 8-bit image, which means each element here, which is called a pixel from picture element, has 2 to the 8 or 1 of 256 values. Okay? So I'll take this image and I will downsample it by a factor of 8 in both the horizontal and the vertical direction. So out of 8 samples horizontally, I'll keep 1. I'll do the same in the vertical direction, or in other words, if you consider here an 8 by 8 block, I will only keep this value and throw away the rest. So I keep 1 and throw away 63. Okay? If I do this, then I end up with a 32 by 32 image, this tiny image shown here. If I bring it back to the 256 by 256 dimension for visualization purposes, then that's how this image will look like. So you see that due to this downsampling, you see these blocking artifacts and these so-called jagged edges, right? They're not straight the edges anymore, but they're jagged. Of course, to upsample the image, I did something very simple. I used so-called zero order hold, which means I just took a 8 by 8 block. I only had this value. I were missing the other 63 values, and I simply gave to the other 63 values the value of this. So each 8 by 8 block has the same value, and this is apparent by looking at this image. This is an 8 by 8 block, for example, and it has constant value or constant intensity. Similarly, the idea of requantization is depicted here. Over here is the 8-bit per pixel image we started with. So here I have 2 to the 8th, 256 different gray values. And while here I have only 2 to the 4th equals 16 values to represent the different intensities. And over here I go down to 2 to the 2nd, that is 4 different values. So clearly you see the so-called contouring effects. They're visible here even, right? So these are, artificial contours or boundaries that have nothing to do with the original image. So you save bits clearly in going from 8 bits to 4 to 2 bits to represent the intensity, but at the same time you introduce errors, the so-called quantization errors.